Welcome back to our series on multivariable calculus. In this episode, we're going to talk about higher order partial derivatives. That is, derivatives of second and even higher order. Well, as you might imagine with partials, it can get a little complicated, much more complicated than taking a second or a third derivative of a one-dimensional function. Let me show you. Suppose we start with f of xy equal to 3x squared y cubed plus 4x cubed y squared. Let's make the y cubed in this one. So 3x squared y cubed plus 4x cubed y squared. Well, let's take a look at the first partials of these. The first partial with respect to x is going to, again, treat the y as if it's constant, so it's going to be 6xy cubed. And then the second term, again, is going to treat the y as constant, so it's going to be 12x squared y squared. Well, let's now take a look at the partial with respect to y, fy. Treating y as if it's the variable and 3x squared as the constant gives us 9x squared y squared. And for the second term, again, the y is being differentiated, so it's going to be 8x cubed y. And that's it. There are their first partial derivatives. Well, you might wonder, how do you go about taking a second partial derivative? And the answer is very carefully. Because this is already the partial with respect to x, I could go ahead and take another partial with respect to x of this function. And that would produce the second partial with respect to x. But I could also take the partial with respect to x of this function, and that would produce what's called a mixed partial. It would be the partial with respect to y followed by the partial with respect to x. Let's go ahead and do both of those. So first, this one, the partial with respect to x. And by the way, that's the notation. You just keep stacking variables as the subscript. Well, now we treat this as the original function, and we simply take its partial with respect to x. That'll produce 6y cubed plus, and again here, we'll just treat it as if the x is the variable, so it's going to be 24xy squared. Well, in the same way, we can take two different derivatives of this one. I can now take this one with respect to x, or I could take it with respect to y. I could go back and take this one with respect to y, now that I've already taken it with respect to x. Let's do both of those. So I'm going to take this one and say f of yx. This will be a mixed partial that involves both the first derivative with respect to y followed by the first derivative with respect to x. It's a second derivative overall, but it's a mixed derivative. Okay, let's go ahead and do it. This is going to produce 18xy squared plus, and again, this is going to be 24x squared y. Well, let's go ahead and do the last derivative with respect to this one, and that is, of course, the second partial with respect to y. So that would be fyy, and that will produce 18x squared y plus, and this one with respect to y is just going to be 8x cubed. Okay, we have one left, and that is to do the mixed partial of this one with respect to y. So that would be fxy. And what is that equal to? Well, with respect to y, this would be 18xy squared plus, and again, this one with respect to y would be 24x squared y. Now, you'll notice something up here, and that is that this particular conclusion and this one are identical. And that was no accident. As long as the original function is continuous, then the second partials, the mixed partials, should always be identical. Because it doesn't matter what order we take the partial derivatives. fx followed by fy or fy followed by fx, a mixed partial should produce the same result regardless of the order. That's called Clairaut's theorem, and as long as the function is continuous, you'll always notice that the mixed partials are identical. And that means we don't have to do it twice. Taking one mixed partial is as good as the other. However, the partials that are true second derivatives, they have nothing to do with each other. Those will always have to be done separately. Now, as you might expect, second derivatives had some huge applications in one-dimensional calculus. Whenever we found a critical point where the first derivative was equal to 0, we could tell whether that critical point was a maximum or a minimum by looking at the second derivative. It told us about the curvature of the function at that point, whether it was concave down or concave up. As you might expect, things are more complicated in two-dimensional derivatives, but we will see in the very next lesson that we can use the second partials and the second derivatives in order to determine whether there are maximum or minimum points on our mappings of these 2D functions.